Greetings, ladies and gentlemen. Today is a little warm-up activity. We were talking about properties of exponents yesterday. I want to talk about scientific notation real quick, and just consider this example. What if I was dividing, I don't know, I'm going to just, well, this isn't even scientific notation, I guess. But if I have 10 to the third divided by 10 to the first, how would I do that? Subtract the exponents, right? So that's 10 to the 3 minus 1, or 10 squared, right? Or 1,000 divided by 10 is 100, right? So I've got some interesting facts for us that I want you guys to ponder here. First of all, do any of you know how many atoms are in the universe?
Trillions, billions, zillions of atoms.
Well, it turns out the estimate for the number of atoms in the universe
10 to the 79.
is 10 to the 79.
We went over this like a few days ago.
Really? Wow.
Yeah.
And that's actually the low end. The high end is 10 to the 81st power. Okay, for the number of atoms in the universe. Wow, good call, man, Mr. Sweeney. So my question is, how much bigger is this number of atoms than this number of atoms? How many times bigger? How could I find out?
Go down the calculator.
Well, let's divide them and figure out how much bigger is that. What would I do with this?
10 to the third.
10 to the second. So I just want to point out that this universe, with that many atoms, could fit 100 of these universes within it. Okay, so they've given themselves some generous room to play with, I think you can tell. Let's see, does anyone know the number of galaxies in the universe?
That would be
100,000.
More than that.
A million.
The number of galaxies is 10 to the 11th power. All right. That's the number of galaxies. Right. So that's the number of galaxies. Do you know how many planets there are in the known galaxy, in our galaxy that have been discovered? Galaxy, not solar system.
Right.
There's only been 350 planets discovered. Only one of them has been found to have inhabitable life on it, or an inhabitable planet that has life, right? Question, comment?
You can finish this, but after I can say something.
Yeah, let's do it. So let's see. So there we go. So how many planets are there overall? If I know the number of galaxies, the number of planets in our galaxy, I could estimate the total number of planets by doing what? Right, 350 times 10 to the 11th, which is, let's see, I've got this written down. That would be 3, 5, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So a lot. I think that's what, 35 trillion is the estimated number of planets that we've got. And maybe at this current rate, assuming that the next planet we find will have life on it, we could assume that 1/350th of those would actually have, if that happened to be the case. Right, so anyways, that's an estimate of the total number of planets. So that's kind of interesting as well. Now, I've got a question. How many atoms are there per galaxy? Well, let's see. Do we have the information I need to figure that out?
So the 350
Times 10.
Wait. Atoms. I didn't mention anything about planets. How many atoms are there per galaxy? So I'm comparing this guy and this guy.
10 to the 11 times 10 to the 11.
Per. What operation does per suggest? Division. What am I dividing? Atoms to galaxy. So I'm going to do 10 to the 79th divided by 10 to the 11th. So what would I do with those exponents? So is that, yeah, 10 to the 68th? This is the number of atoms in a galaxy on average, I imagine. So interesting facts there. So what's up?
Okay.
Comment, question? Yeah.
Yeah.
Chime in.
What if, think about it, there's another planet with life on it, like Earth, and there's people, but we haven't found them because we haven't found their galaxy, and they're like so far away from us that we can't find them. And then we
Okay.
That could be
Okay.
true. Like, what if
All right.
like two spaceships like pass each other?
Oh, and we just missed. Oh, that would have stunk. Oh, that would be terrible. But, all right, yeah, okay. So, yeah, that's what we're considering some of these facts here. I've got a probability fact for you guys. So one protein molecule, right, formed up of different atoms and such, the probability of a single protein molecule forming. Did I spell it? Oh, did I mess up my I and E? All right, whatever. Molecule forming on planet Earth using all of its atoms across the entire, or for all time that Earth has existed. All right, so Earth has an age, Earth has a number of atoms. Protein molecules are complex structures. And if all of those atoms on Earth keep bumping into each other, what's the chance that a protein molecule would just by chance happen to come out of that random jumble? All right, here's that probability. It is 1 in 10 to the 161st power. Which, I want to point out, so the probability of one protein molecule forming on Earth using all of the atoms for all the time that Earth existed, just one would be this probability. 10 to the 161st power is bigger than the number of atoms in the universe. All right? Think about if I, right, had the number of atoms in the universe and I marked one secretly, and then I sent you out into the universe and I told you, see if you can by chance guess which atom I picked. All right? And you'd be like, is it this one? And I was like, no. In fact, you're billions of light years away. It was this one way over here. And it wasn't even that kind of atom. I chose, I don't know, a hydrogen atom. And you didn't. You know, like, it would be a shame. You know, you probably wouldn't get it right. This probability is more difficult than that. In fact, we could find out how much more difficult. Let's put this in comparison. What is 10 to the 161 divided by 10 to the 79? Is that 10 to the 82? Did I do that right? Oh yeah. So, all right. By the way, this is bigger than the number of atoms in the universe. So catch this. Imagine our universe, all right? Huge, right? Huge. Imagine every atom in that universe. Zoom in on one of those atoms, ready? So we're zoom in your mind. One of those atoms, super tiny. Replace that atom with another universe of atoms. Okay? And then do that with every atom in the universe. Okay? So the number of atoms in our universe, replace every atom with another universe of that number of atoms. Way bigger, right? Way bigger. And now I'm going to mark one of those atoms, and you have to find the right one that I marked in that large number. That's the probability of a single one protein molecule forming on Earth using all the atoms for all time that Earth existed. Turns out, bad news, life requires more than one protein molecule. Life requires 239 of them. So the probability of 239 protein molecules forming on Earth using all of the atoms and the time that Earth has existed, so 239 protein molecules forming the correct ones that are required for life, so not even arranging themselves into the order of life, just existing on the planet, so they'd still have to be close enough to each other that they could somehow form some sort of bacteria, is 1 in, ready, 10 to the 119,879 power. Now, I just want to point out how, let's see. Okay, so here's a probability of enough molecules forming for life to exist on our planet for the entire time that our planet has existed.
Waldo.
Oh, is there a good Waldo?
Thing, like,
Yeah. These are probabilities and statistics and
I see it.
estimations. Yep. So yeah, right here and right here is a good Waldo right there. So now this probability, you might be like, yeah, but there's lots of planets, so that's going to cut that probability down, right? Maybe. How many planets were there?
I think there's only 8 of them.
There's only 8 planets.
That's what I thought.
Well, in the galaxy, solar system is 8. Solar system is 8. Galaxy is the whole Milky Way. All right. I'm going to show you some graphics from online in just a moment. But let's see, 350 times this. I'm just going to count. Let's pretend 350. Let's just call that 1,000, just to make the math a little easier. And I think you agree. I'm rounding up there, right? But yeah, like it's almost 3 times as much. But that's fine. Whatever. We're rounding here. So that's 1,000 is the same as 10 to the third. So 10 to the third planets in our galaxy multiplied by the number of galaxies. What would I do with those exponents? Atom, right? So 10 to the 14th. Atom. I like it. That's pretty clever. So anyways, so that's the number of planets, an upper end of it. That's 3 times as many planets as they're actually estimated. So 10 to the 14th. So if I took this probability, and I understand planets are different sizes and such, so if I do 10 to the 14th, the number of planets, multiplied by this probability, 10 to the 119,879, what would I do with those exponents? Well, I could put this over 1, and that's the same as 10 to the 14th over 10 to the 119,879. So this is a common argument. People are like, well, there's lots and lots of planets out there, so it changes the probability. It helps it out. So it's like way different now, right? But what would I do with these exponents? I'd subtract them, right? And in fact, let's see, what's left on top would be 1, and then I'll have 10 to the, and I'll subtract the 14 from this number, and I get 119,865. Did that help our probability a lot? Well, it helped. I mean, 10 to the 14th power is a big number, so it's that much more likely. But I just want to point out that this is, oh man, still really bad news. Probability of all planets developing just the 239 molecules over the time of that happening. I mean, maybe I'd have to multiply in some factors. I would help a little bit figuring out the age of the universe and stuff. I think, what is that, 10 billion? I don't remember. I'd have to look it up. But even 10 billion is only going to subtract like, what, 9 or 12 from this number. It's still not going to make a huge dent in it. So that's kind of bad news there. Well, that's obviously up for debate. But yeah, so this is kind of interesting. To figure out a scale of how rare this would be, let's figure out how many times could I divide 10 to the 119,865 by the number of atoms in the universe. All right, so how many times could I divide it by 10 to the 79th power? All right, so divide it once, I'd subtract 79. Divide it another time, I'd subtract 79. Divide it another time, I'd subtract 79. So repeated division, right? So I'll just say many times. How could I figure out how many times this could be subtracted from that number?
Do it on a calculator.
Do it on a calculator. Oh, so you just want me to do 119,865, subtract 79, and hit enter, 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 enter?
Oh,
What's a better way to do that? What's repeated subtraction the same as?
divide.
Division, right? So I'm going to divide that by 79, and I get, so ready? This is 10 to the 1517 right there, okay? Now that is, let me explain what we've got here. So right, I explained the number of atoms in the universe, right? And I explained the idea of what if you zoomed in on one atom and replaced it with the number of atoms in the universe, okay? And then let's take one of those new atoms, we'll zoom in again, and replace that with one of those, another universe with that same number of atoms. And we'll zoom in again, and replace it, and zoom in again, and replace it, and zoom in again. The number of times you would zoom in and replace is this number here. Okay? So that is not the number of atoms I'm talking about. That's the number of times I've replaced the atoms in the universe with another universe. And now take those new atoms, we'll mark one, right? And I'm going to send you out into this universe of universes, and you're going to find the exact atom that I marked. And you will have a very hard time. So that's the same as that particular probability. So anyways, so there's some good old probabilities, properties of exponents, and sizes of things. So there you go. Just some interesting thoughts, some facts thrown together there. Have fun, internet friend.